Okay, this is our Math 2460 first Zoom session of the week. Just to let everybody know what we were talking about, people were asking about their grades on that proctored test, and we will report those on your spreadsheet, and that test 2 grade will appear in your proctored test column. So I've got a few participants here. Did y'all have any questions or anything you wanted to ask? Or do you want to charge into this week's work, which is section 8.2 and 8.3?
I'm good with last section. I think this week's section is good if we go into that.
All right. Chapter 8. This week we're doing 8.2 and 8.3. All right. Chapter 8, they call it Techniques of Integration. Can't even spell integration. Got it right here. R-A-T-I-O-N. Golly, not a good morning this morning. Okay. You could technique called tricks. And I could show you all the names of them, just thumbing through. 8.2, just to summarize the whole chapter, 8.2 is called parts. And this integration by parts is the full name. You can see it, integration by parts, or just generically parts. It undoes the product rule. And 8.3, hopefully we'll have time to get to a few of those. These are powers of sines, cosines, tangents, and secants. Trigonometric integrals, they call them. Trig integrals. 8.4 is called trig sub. So 8.3 and 8.4 really hit your trigs. And 8.5 is called partial fractions. Partial fractions. I can give you the forms of these things as we're going through. There we are, up to 8.5. I hope you're breathing hard because you are now on the top of the mountain of difficulty. Though, in terms of, if you drew a graph of difficulty, at 8.5, probably at 8.4, you're on the peak. 8.2, you're climbing the mountain at 8.2 and 8.3, and you're at the peak of difficulty. This is difficulty. Get past 8.5, and we're doing something called numerical. Probably the easiest section of the entire class, if you know your formula. That's so 8.6 is called numerical integration. 8.7 uses tables of integrals. Basically, you're almost copying your answer out of a table, but it's not quite that easy. And 8.8 is called improper integrals. If you ever wanted to do something improper in math class, something naughty, this is your section to do it. I hate the word improper. It makes you, of course, it wouldn't matter today. We're online. I'm not using a camera, but it makes you feel like you're ready for class. You're doing something like stripping or something in front of the class. You're doing something really improper, and you're not. It refers to something. But in any case, to me, it's bad terminology. But in any case, yeah, you're down the numerical 8.6, 8.7, and 8.8. You're down the lower slope of difficulty. So that to me is the way the chapter works. And yeah, we'll be sucking wind around 8.4 and 8.5. working out those tricks. Pages and pages of work, 2 or 3 substitutions deep. But let's enjoy something easy at the beginning here. 8.2, integration by parts. All right, again, it undoes product rule. In other words, you know what a straight e to the x looks like, right? Just to remind you some simple ones, e to the x plus c. And you know what a straight x does. On a polynomial, you add 1 to the power, divide by that, plus c. But I know you've laid awake nights wondering if you put it together, what integral x e to the x is. Well, you just can't take this and multiply it by this. You can on limits, but not on integrals. It's just not the product of this and this individually. So I know you've laid awake nights wondering, gee, what would happen if I stuck those 2 things together? So I'm here to satisfy your incredible curiosity. All right, go to product rule. The book uses u's and v's. If I went d dx of u and a v, everybody remember you would go first, derivative of the second, we'll call it dv, plus second derivative of the first. Remember you're listing first, d second, plus second, d first. Does this ring a bell? Product rule for derivatives. Everybody's gone silent.
Yeah, I remember this.
Yes, for Calc 1.
For Calc 1, right. So take integral both sides. So integral of duv dx, integral u dv plus integral v du. This side undoes. And we're going to solve for this. And do you see all I got to do is subtract this, subtract integral v du, subtract integral v du. So over here I get uv minus integral v du is equal to integral u dv. They usually switch it around. Integral u dv, uv minus integral v du. And if you look on page 523, right here, u dv is u times v minus integral v du. How do we use this formula to solve the integrals in this section? Hell if I know, I never use this crap. It's complete gibberish to me. So let me show you, it basically just names the scheme you need. So let me go back to our first example because it's about the easiest. I think it's example 1, in fact, might be. It is. In fact, this is example 1. Let me go back. It's about the easiest thing you can do with this. And then, yes, further in there's more tricks that make it a little tougher. So this is example 1. Evaluate or find integral of x e to the x dx. All right, now I'm going to keep the scheme. We're going to follow the scheme. I'm trying to keep the scheme visible. What you do is literally you have two parts most of the time. I'll show you the trick if you don't have two parts. You have two parts. One you call u and one you call dv. 90% of the time you want your u to be the polynomial, but 10% of the time you don't. So we'll point those times out. In other words, I'm going to call u equal x and dv equal the e to the x. I'm forming a 2x2 matrix. You get the first row of the matrix by naming your parts, these things. Get your second row by doing the operation. In other words, you get your cell over here by differentiating. So du is a straight derivative of x. It's 1 on this case. Here you do, in this column, you do the antiderivative, and that's pretty simple, a straight e to the x. We don't write down the plus c here. That'll come at the end. You just do a straight antiderivative and ignore the plus c inside here. So first column, differentiate. Second column, anti-differentiate. And you form your 2x2 matrix. But first time through, I know it looks like real gibberish, but trust me, these about, except for 8, whatever I said there, 8-7 or whatever it was, numerical integration. These are about the easiest problems because the scheme works the same every time. After you do about 3 or 4, you'll get used to the scheme and crank them out pretty quick. We're now going to follow the scheme. I don't pay any attention to this side. You want to form u times v. That's the cross product. So in other words, my integral of x e to the x dx, I'm trying to follow u times v minus integral v du. Well, this u times v is this cross product. You just write down x e to the x. That's multiplying the u times the v. Then minus your integral of v du is the integral of your bottom row, e to the x times 1. You just put a dx. It looks proper. So bottom line, you take cross product minus integral bottom row. Now, the idea is the integral of the bottom row is supposed to be easier than your original. And you can see it is. The x is gone from it. And this, you can work this straight out. So straight integral e to the x. So your bottom line, you're going to get x e to the x minus an integral e to the x is also e to the x. And now you add your plus c because you got your full answer. And you've undone the product that was here, and this is the function, it's the antiderivative of this. Do a derivative on this, and I should give back this. And I'll do the first one for you just to try to give you some confidence in this gibberish. So here's your check. Take d dx of x e to the x, subtract e to the x, add c, and we better get back the original e to the x. If we don't, I'll quit on the spot. Okay, well, this is a product. Works by product rule. First, derivative of the second, e to the x, plus second, and d first, 1. All right, then you go to this term. Well, that's a straight e to the x, so its derivative is also e to the x, and your c goes away. You have your lead x e to the x, and your e to the x minus e to the x just cancels, and you wind up with your x e to the x, which is what you had originally. I don't hear any oohs and ahs. Does anybody want to ask about any of this or go back through it?
Wait, so we can check our answer by derivative back?
Absolutely. Or you can use the back of the book. The more complicated ones, you'll probably want to use the back of the book. I was just trying to give you some confidence in this, that you do wind up with a function that when you differentiate it, you get back the original. That's why it's called the antiderivative. This whole chapter we're going to be doing, it's not calculated work, there's no numbers. We're just going to be finding antiderivatives. There's 8 sections in this chapter, 8 different ways of finding antiderivative. In fact, that's a lie. The only numbers in the section are it was 8.7 there, that numerical integration, that's all numbers. But the other 7 sections, there's no numbers. Did anyone want to ask about any of this? Let's, just to do another one, let's try x sine. Integral x sine of x dx. All right, I'll try to shorten it up a little bit. You want to form your matrix. So again, this is going to be an 80% case. Your u would be your x and your du would be 1. Straight derivative. The dv would be sine. V would be antiderivative on sine. Looks like it'd be a negative cosine. Any questions? That's what you do on all of these parts problems. Form this matrix. Name one part your u to differentiate. Name one part the dv to anti-differentiate. We lose anybody doing that? I'll write it down in words. So now what you want is the cross product. God, I'm not having a good day. Cross product minus integral bottom row. So cross product would be, you can do it in any order you want. I mean, I guess I'll write negative x cosine x minus integral, and the bottom row is negative cosine x dx. I could put times 1, but we have to. And notice you can get a little tricky with the signs here. There's a negative in the formula, and then the bottom row has a negative. So if you want to clean it up a little bit, negative x cosine x, add integral cosine x dx. And you can see you've traded your original integral for an easy integral. Negative x cosine x, add sine x, plus c. Anybody want to see that? Take a derivative on that? Or do we all believe that if I did a derivative, I'd come back to this? Silence. So odd, no one can speak.
Yeah, could you actually do the derivative of this one?
I would be thrilled, yes. So check. Derivative of negative x cosine x, add sine x, plus c. So you would get first, derivative second, derivative cosine's negative sine, plus, are we going too fast? First, d second. Yep. Second, d first is 1, negative 1. Let's see, so I'm going first, d second plus second d first. Then I go to this term, that's a straight sine, derivative is cosine. C goes away. And there you are, your negative x, negative sine x, that's your x sine x. And your negative cosine plus cosine, that cancels, and you're left with your original. Did that prove anything to anybody or only to me?
Yeah, that makes sense.
Okay, but this is the scheme. It's very, very repetitive scheme. Are you ready for the tricks?
Yes.
Okay. They show you some tricks. I'll start off with some easy tricks rather than them. Like one of their examples is x squared log. We're not quite ready for x squared log x, but first trick, tricks. Example, integral log of x dx. Okay, you haven't done a straight log yet. Okay, now wait a minute here. We're supposed to be parts. That's plural, 2 parts. I only see 1 part. Oh no, what am I going to do? Okay, well, here's the first trick. If you only have 1 part, you can form a second part by what? Multiplying by 1. Haven't changed anything, and now you have 2 parts. This is going to be a 10% case. You see, you don't want your u to be 1. What's your du? It would be 0. And you've killed your bottom row. So this is a case you actually want your u to be the log. And your du, derivative of log, was 1 over x. Hope you all know all your derivative rules. They're going to come back on you. So 1, it turns out, is an extremely simple polynomial, but it is a polynomial. Numbers are polynomials of degree 0. Your dv is 1. Antiderivative brings back the x. Questions about that? Can I just write down go straight to the answer, or do I need to keep showing you cross product minus integral bottom row?
Now let's just go straight to the answer.
So cross product makes x log x minus integral, and bottom row is 1 over x times x dx. Literally take what's in the bottom row and multiply it in an integral. And the idea is that it's supposed to come out simpler, and can you see it does? The x's cancel. Write out real slow. X log of x minus integral of 1 dx. That'll be the second time we've done this integral. You did it up here, and now you're doing it here. That's x log x minus, bring back the x, and plus c. Anybody want to see the derivative done on that to prove it comes back, or do we believe by now?
I believe you.
We believe. Okay. Always like to convert my infidels. We now believe, yes. If I did a derivative, you'd do a product rule on this, it would have a term canceling this, and you'd come right back to a straight log. Okay, the same trick works on, say, an arctangent. Example. Integral of arctangent. Again, if you only get 1 piece, multiply it by 1. Make your u arctangent. Make your dv the 1, which makes the v the x. Do you remember your derivative of arctangent? This is where you got to remember your derivative. Some of these derivative rules we gave you this semester. Chapter 5, section 5, 8, I think. Y'all remember your derivative of arctangent? Or has that been flushed?
No, but I can find it somewhere.
Okay. I believe it's section 5.8, which is another good signal I need to retire right now because I am getting the book memorized. If you teach so long, you get the book memorized. You fill in your head with this crazy stuff.
Derivative u divided by u plus u squared.
Right, and then that's showing you a chain rule form of it, but in effect, we'll tell you 1 over 1 plus x squared with no chain.
Okay.
Now, they showed a u prime over 1 plus u squared, and yeah, that's the full form if that's not an x, because that u prime is your chain rule term. But we'll just keep it really simple like this. So I go cross product, and that would be an x arctangent x minus integral, and bottom row, can you see the x would stay on top? I'm going to go x over 1 plus x squared dx. Questions about this? Yeah, I could have written 1 over 1 plus x squared times x. I just kind of crushed it together. Now, without the x, no x, you've got an arctangent. But with the darn x, you see how you got a u du? So this one you can't really write down. This one's a u du integral. These techniques come up randomly in the middle of all these problems. Your u is going to be 1 plus x squared. Your du, 2x dx. So you're going to throw in a 2, fix it with a 1/2. Everybody remember doing this? And done one in a while.
Yeah.
Same technique. You just got to recognize when it comes up. You got an x here for a derivative on your x squared here. So you're going to get x arctangent x minus 1/2 integral 1 over u du. Your 1 plus x squared, you got your 1/2 for a fix. The 1 plus x squared is your u on bottom. And your 2x dx is your du. If you're really good, you probably could have done that in your head. You see how it's going to be a log. Go to the next page. So I'm going to get x arctangent x 1/2 log, we use an absolute value, u plus c. And the u is 1 plus x squared, so x arctangent x log of 1 plus x squared plus c. That would be a little longer to differentiate and show you get back the original, but I would be thrilled if anybody wants to see it, or if you're now believers, you can check the back of the book. Questions about that?
Nope.
Okay. You want to pick some off the homework?
Yeah.
Okay. Let me show one other trick before we do off the homework. Here's a basic trick. Let's keep it really simple with x squared e to the x. So example, another trick, integral x squared e to the x. Same idea, u is your x squared, du, 2x dv e to the x, v e to the x. Cross product. Hope you're getting used to this by now. Cross product minus integral, bottom row 2x e to the x dx. Have we lost anybody? Cross product minus integral bottom row. Now notice what happened. You started with an x squared and you wound up with an integral 1 power lower. That's called reduction, power reduction. I can't really do this straight because guess what? I've got another product. Oh no, what am I going to do? Well, guess what? Guess how I got to work this out?
Do it again.
Yes, this is, you want to call this tricky, give this trick a name, it's called parts twice. Guess what? If I'd started with an x to the third, I'd be doing parts 3 times, x to the fourth, parts 4 times. Triple your fun, quadruple your fun. So yeah, because every time you do a part, you only lower the power by 1. So you got to keep working it down until you finally get to a straight integral of e to the x. Now the 2, I could put it out, then I got a distributed problem, or I can leave the 2 in and just use it as my u. du is 2. The dv is e to the x, and v is e to the x. Now, what you got to watch, though, is distribute problems, because this parts always gives you the 2 pieces. Cross product minus integral bottom row, and that minus sign in front of the whole thing is going to distribute through it. So you really, if you don't pay attention to your signs, really screw things up. Even I can do it right in front of you, so I got to be really careful with it. Minus big parentheses. Cross product minus integral bottom row. There. And now I've gotten rid of the x. I'm going to go ahead and distribute my minus sign. Minus 2x e to the x and add integral 2 e to the x dx. And now I can do this integral pretty simple. 2 just carries along, and I wind up with e to the x minus 2x e to the x and add 2 e to the x plus c. And yeah, to check this with a straight derivative, you got a product rule here, you got a product rule here. That's a straight 2 e to the x, and combine all your terms, and you should come right back to this. But probably by this time, it's much easier to use the back of the book. Questions about this? I don't know if you want to couple out of the homework, and then we can do 8.3, charge into 8.3. Homework starts, I let you out of the very beginnings. They give you really baby ones. They just want you to identify your u and dv, but do not integrate. I let you out of that. Here they tell you to find your integral. I got my assignment in front of me. Where did I start it? Started at 11. Yeah, so I did start it here. They're trying to help you here on the first 2 by telling you what your u and what your dv should be. I would ignore that dx there. I just use just do these straight the way I've showed you. They're telling you u is x cubed, u is actually log, and the dv is x cubed. So you're actually going to differentiate your log on a log and anti-differentiate your x cubed, raising the power. Some stuff like 15, when they throw coefficients in at you, then you got to pay attention to chain rules, and the numbers can drive you nuts. You want to see an example of something like that?
Sure.
Okay. You wouldn't think it'd be that complicated, but actually throwing coefficients on you can drive you nuts. So this is 15, it's off page 529. Integral of an x e to a 4x dx. All right, see, in all my examples, by keeping a straight x, I've ignored chain rules. But you want your u to be x, your du to be 1. Your dv would be e to the 4x. Now, if you really want to be painfully anal, see, you will write out, to get your v, you'll write out integral e to the 4x dx, and it's actually a u du by itself, and I've frozen. Okay, here we are. And I've actually frozen. I'm not frozen. I've actually, if you want to be painfully anal, you write this out. Your u is 4x, your du is 4 dx, etc. And you'll get there. If you can do this in your head, you can really shorten it up. You get an e to the 4x. The question is, where's the 4 go when you anti-differentiate? Anybody have a clue? See, when you do a derivative, you multiply by the derivative 4x, which is 4. Anti-differentiate, guess what you do with the 4? You what? You divide by it. Now, is that obvious or only obvious to me?
Well, you kind of do that with normal just integration, so
Yeah.
that's pretty consistent.
Pretty consistent, okay. But just remember, you're going to divide by the 4 when you anti-differentiate here. Again, you could show it with the u du. But if you got to write out the u du to go from here to here, you just, lengthen the whole thing. All right, so if everybody believes this, same scheme, cross product is x, e to the x, 4x divided by 4, minus integral, and your bottom row is e to the 4x divided by 4 dx. Again, multiply by 1, but it doesn't change anything. All right, see if you can finish, because this will be the second time you've done this. Now, you've already got a 4 here, so you're going x e to the 4x over 4. I'll write a 1/4, pull that 4 out, and when you do this e to the 4x, you get e to the 4x, and guess what you do with the 4 again? You what by it? You
Divide.
divide by it again. So that's the second time you do that operation, integral, in this whole problem. You do it here to here, and you're doing it here again, but you already got a 1/4 coefficient because you already did it once here. So you're going to get a 1/16 finally. X e to the 4x over 4, or you put a 1/4 in front, and you're going to minus a 1/16 e to the 4x plus c. Because you wound up doing an antiderivative e to the 4x twice in the problem, giving you a factor of 1/4 each time. Questions about that? Let's see, we're almost 40 minutes in, probably need to get on to 8.3. Notice in their directions, I'll just point this out, they're telling you flat out, find your indefinite integral, solve by the simplest method, and not all require parts. Some are simple UDUs, if you can spot it. It goes all the way up to this column right here. I think it stopped at 33. 33 is a granddaddy problem. That's another trick. I already did 31 for you, straight arc tangent. If you took any notes or rewatched the video, I did the straight arc tangent, multiply by 1. And so if that's straight problem 31. 29, you'll be here a while. Parts 3 times. You get 29. But we'll help you out on Thursday. Or if you got any questions before then, you can email me. Real quick to 8.3. Trig integrals. You can see the title. Trig integrals. Okay. Time I get all the formulas down here, I may not have time to work too many examples from this. Trig integrals. Okay, again, the super simple one's a straight sine. That should be a negative cosine. A cosine should be a straight sine. Let's see again, derivative cosine's a negative sine with a negative gives you positive sine. Derivative sine is cosine. All right, but in this section, you get powers of trigs. Example, I'll just write down example 1. Integral of sine cubed cosine fourth x dx. So you can have arbitrary, you'll have products of these and arbitrary powers. This does not work by parts. That's why it's in its own section. It's got its own technique. Let me point something out though. The reason this is, I hate to say screwed up or needs a really more complicated technique is because they've given you a second power on this cosine. Let me just point something out because they will do this to you. Just for an example, what if it was integral sine cubed and a straight cosine? This is a u du. Okay, make your u sine, du is cosine, and you have an integral of u cubed and du. That's cosine x dx. U cubed, u is straight sine, so sine cubed is u cubed, and this is your du. And you get u to the fourth plus c over 4. And that is sine to the fourth of x over 4 plus c. So they will mix some of these in on you, and if you can spot it, you don't have to do what they're doing in this section. But by raising that to a fourth power, they've totally screwed this up. This doesn't work. All right, how does it work? I know you're dying to know. Look at this gibberish. You get 3 guidelines. It's about reading whether the powers of sine are odd and positive, whether a power of cosine is odd and positive, that's case 2. You do this gibberish, you do this gibberish, and if you have even powers of sine or cosine, you play these identities. And it's tough, I don't have enough time to show you every single case, so we'll have to save some of them obviously for Friday. But let me show you at least the first case to show you what you're doing. Sine cubed and a cosine fourth. All right, look at guideline 1. Power of sine odd and positive. See how that fits here? Your power of sine is odd, it's 3, and it's positive. All right, so what they're saying to do, I can get the book clear again. They're talking about saving one sine, convert remaining factors to, I believe it says cosine. Here's what that means. Save one sine means move one sine to end. All right, here's what that means. That means you get sine of x and you move one sine to the end with the dx. Well, when you do that, you've reduced that power by 1. That becomes a sine squared, cosine fourth. I'll just lay this out step by step. Probably the only one we'll have time to do. Any questions about doing this? This is what they mean by save one sine. The logic to this is that this is eventually going to form a du on a udu. We're eventually moving to a udu on this, but we've got to play these identities. So this is what save one sine means. Any questions about that?
Nope.
Okay. Convert remaining factors to cosine basically means use your identity. Everybody remember that a sine squared can be written as 1 minus a cosine squared?
Yeah.
Because sine squared plus cosine squared is 1. So sub in, and you get integral 1 minus cosine squared, and you've converted the remaining factors to cosine. You have your cosine 4. Didn't have to convert it. It was already cosine. Sine x dx. All right, everybody see I haven't changed a thing. This minus sign means I can bust this into 2 integrals. Bust into 2 integrals. In effect, distributing this from the back side. So I get, this will be the last line I'll get on this page. Integral, see, when I multiply this by 1, I get cosine to the 4 sine x dx minus integral cosine to the 6x sine x dx. Any questions about that? All of that times the 1 straight integral. And my cosine 4th, cosine squared is my cosine 6 sine x dx. Questions about that? I have now converted it to this situation. It's just that my u is cosine. See, my derivative, if I make my u cosine, my derivative is a sine. Yeah, I know there's a negative, but and same thing here. U is cosine, derivative is a negative sign. I can fix the negatives. And that's what you do next then. U is cosine, du negative sine. Same thing here. Cosine, du negative sine. Let me keep this visible. I'll rewrite it down here. So I started with, I'll just rewrite the line. Cosine 4th sine x dx cosine 6x sine x dx. And if my u is cosine, my du is negative sine, then I need a negative in here and a negative out front. And same thing here, u is cosine, negative sine. Then I will need a negative here and again a negative out front. And I already have a negative, so that 2 negatives there, I'll turn positive. Lost anybody? When I sub in, I get a negative, an integral u to the 4th and du. See, all of this is my du. And I get a u to the 4th. Here I get a plus u, integral u to the 6th and du. All of that is du. Have we lost anybody?
Nope.
All right. Anybody out there think, golly, if this is the simple ones, what's okay? Believe me, there's a lot tougher ones than this coming up. Coming attractions. All right, so these are really simple integrals to do now. Add 1 and divide by that. So that's a negative u to the 5th over 5. Add u to the 7 over 7 and plus c. And in both cases, your u is cosine x. Negative cosine to the 5th x over 5. Add cosine to the 7th x over 7 and plus c. I doubt you want to see me actually differentiate that and prove it goes back, but you can check the back of the book. Unless they really messed around with it. That should be pretty close to what they have. This is 8th. Actually, I worked out example 1. Okay, actually I did work out, this is example 1. So actually, yeah, that's exactly what they have here. We're at 50 minutes, so I'll just point out there's actually 2 more groups of problems in this. They give you powers of tangents and secants. And again, there are five guidelines. 5 guidelines. You got to look at what they give you and decide if your secant's even positive, do this. If your tangent's odd and positive, do this. Those secant factors power the tangent is even and positive, do this. If you get a straight secant power, do this. And number 5, try converting the sines and cosines. They left off guideline 6. Guideline 6 is dial a prayer. But there's also a 3rd group of problems. And these are actually the easiest ones in the whole section. If you get straight products of sines, sine or cosine, you use these identities. They should have showed you these in trig. If you actually have those memorized, I would be very impressed. And you sub in these identities. And these are actually the easiest ones of the whole section. There's a little group toward the end that I assigned that use these identities. 51 minutes. You all want to call it and we'll come back on Friday?
Yeah.
Help you out with anything?
See you Friday.
See you Friday? That's a lot of stuff to throw at you, so good luck.
Thank you.
Thank you for coming out, and we'll see you again on Friday.